Now welcome to the third chapter, it's Newton's laws of motion. Now imagine this rock resting on a horizontal table. What would happen if you leave it for 10 minutes? Nothing. The rock remains in the same position. Even if you leave it overnight, the rock won't move on its own. And so it's common knowledge today that an object can only be set in motion when a force acts on it. Therefore, the rock cannot move unless you push it or pull it. Similarly, a force is needed to change the speed of a body or stop it. We defined a force as a push or a pull and said that a force can, among other things, make a stationary body move, bring a moving body to a stop, or change the speed of a moving body. The three Newton's laws of motion are based on the effects of force on motion of a body. Newton's first law. Look at this demonstration. There is a glass tumbler on the table over which is placed a cardboard. Now place a coin on the cardboard. The tumbler, the cardboard and the coin are all at rest. Flip the cardboard and see what happens. You will notice that the coin falls vertically downwards. The coin does not move with the cardboard but falls downwards, however, due to the force of gravity. The coin does not move with the cardboard due to a property of matter called inertia. Inertia is the inability of a body to change by itself either the state of rest or of uniform motion along a straight line unless an external force is applied on it. The property of inertia applies for all bodies at rest or in motion. Again, here you can see the passengers in the bus leaning backwards when the bus suddenly starts moving. This happens because the upper part of the body continues to be at rest due to inertia, while the lower part starts moving along with the bus. Equally, when a moving bus stops suddenly, the passengers jerk forward. This is because the upper part of the passengers continue to move while the lower part of the body comes to rest along with the bus. Newton's first law of motion is also called the law of inertia and states that a body at rest stays at rest. A body in motion stays in uniform motion in a straight line unless compelled by external forces to act otherwise. It is quite obvious that stationary objects do not move on their own, but it's hard to think that a moving body will stay in motion forever. And the reason it does not happen is because unseen forces act on the body. For instance, the force of friction always opposes motion and slows down a moving object and eventually comes to a stop. In fact, the rock on the table can be moved by a force that you cannot see. If you do this, for instance, when you do that, the force that moves the rock is the force of gravity. Actually, gravity was pulling on the rock all along, but when the table was there, that kept the rock from moving down. When you remove the table, you allow the force of gravity to move the rock down. And so according to this first law of motion, in the absence of all external forces, a body will never change its state of motion. Momentum. Imagine if you applied brakes on a large and heavy truck. You realize that it will take quite a distance to bring the truck to a stop. However, a small and light car would come to a stop over a short distance upon application of brakes. The bodies have a quantity called momentum, which depends on the mass and velocity of the object. The momentum of a body is defined as the product of its mass and velocity. If m is the mass of a body in kilograms and v its velocity in meters per second, then momentum is equal to mass times velocity. P is equal to mv. The SI unit of momentum is therefore kilograms meter per second. Momentum is a vector quantity having both magnitude and direction. The direction of momentum is the same as that of the velocity of the body. For instance, if a car weighing 3,000 kilograms is traveling at a velocity of 72 kilometers per hour, we can calculate its momentum. Mass of the car m is equal to 3,000 kilograms. Velocity is equal to 72 kilometers per hour. We convert that into meters per second and it's equal to 20 meters per second. Momentum is mv, 3,000 times 20, which gives us 60,000 kilogram meter per second. Newton's second law. So we've seen that momentum will occur if we have an object that is in motion, and to calculate we simply multiply the mass and the velocity of the object. The greater the mass, the greater the velocity, the greater the momentum it's gonna be. And so to change our momentum, what we can do, we can change the mass or change the velocity. And the easiest way to change velocity is to apply a net force on that object. If we apply a net force to the right, we'll see an increase in momentum towards the right. Okay? Let's say it's moving towards the right and we change that net force. What will happen? It doesn't happen instantaneously, but what we will see is a change in momentum. And so we have said that momentum is equal to mv. And so if a 1 kg cart is moving with a velocity of 2 meters per second, its momentum will be 2 kilogram meter per second. And so if we increase the velocity to the right, we will increase that momentum. Another thing you need to know is that the net force on an object is going to affect that change in momentum. So let's say we have a card like this. It's at rest, it has no momentum, and we apply a net force to it, say by connecting it to a weight. Now we apply a net force to the right. What's gonna happen to our momentum? It will increase to the right. What happens when we increase the net force? If we double the net force on the object, the momentum will increase. Triple it, and we shall see an increase in momentum. And so it's a direct relationship between the net force and momentum. And this is the basis of the Newton's second law of motion. Newton's second law of motion states that the rate of change of momentum of a body is directly proportional to the resultant external force producing the change and takes place in the direction of the force. Thus, resulting force acting is proportional to the rate of change of momentum. If the forces acting on the body are in equilibrium, that is balanced, then the resulting force acting on the body is zero, and hence there would be no change in momentum. This implies that the body under this condition will continue in its state of rest or uniform motion in a straight line, according to Newton's first law. Now, consider a force F acting on a body of mass m for a time t. If the velocity changes from u to v, then change in momentum is equal to final momentum minus initial momentum, that is equal to mv minus mu. Therefore, rate of change of momentum is given by change in momentum over time taken, that is equal to mv minus mu, the change in momentum, over t. From Newton's second law, force is proportional to the rate of change of momentum, that is F is proportional to mv minus mu over t. Factorizing the right hand side, F is proportional to m into v minus u, everything over t. But then, V minus u over t is equal to acceleration, and therefore force is proportional to mass times acceleration. So F is equal to K ma, where K is a constant. The Newton is that force which produces an acceleration of 1 meter per second squared when it acts on a mass of 1 kilogram. This definition gives F is equal to 1 Newton, A is equal to 1 meter per second squared, and M is equal to 1 kilogram. And therefore, substituting in F is equal to Kma leaves K is equal to 1, and therefore F is equal to ma. Force is equal to mass times acceleration. An example. A force of 125 newtons produces an acceleration of 3 meters per second squared on an object. Calculate the mass of the object. In the solution, force is equal to mass times acceleration, and therefore mass is equal to force over acceleration, which is equal to 125 over 3, giving us 41.67 kilograms. Another example. A 1,200 kilograms car starts from rest and attains a velocity of 45 meters per second in 9 seconds. Calculate the average acceleration of the car and the average force applied on it. In our solution, since the car starts from rest, u is equal to 0. Acceleration is equal to v minus u by t, which is equal to 45 minus 0 over 9, and that gives us 5 meters per second squared. From the expression F is equal to ma, force is equal to 1,200 times 5, which gives us 6,000 newtons. Impulse. When a force acts on a body for a very short time, the force is referred to as an impulsive force. The result produced is known as the impulse of the force. Impulsive forces occur when two moving bodies collide. If a force F acts on a body of mass m for a time t, then the impulse of the force or the impulse is given by force times time. That is, impulse is equal to Ft. From Newton's second law, F is equal to mv minus mu over t. If you do cross multiplication, this can be rewritten as Ft is equal to mv minus mu. Since mv minus mu is the change in momentum produced in the body during the time t, the impulse of a force acting on a body during a given time interval is equal to the change in momentum produced by the body in that time. The SI unit of impulse is Newton second. Therefore, another unit of momentum is the Newton second. Since the rate of change of momentum is equal to impulse, that is Ft is equal to change in p, then F is equal to change in p over t. Thus, a force can be defined as the rate of change of momentum. A plot of F against t is as appears on your screen. The area under the curve is Ft, or change in momentum during collision. And so once again, impulse is equal to the force applied on an object times the time the force is applied. This impulse is equal to the change in momentum of the object. The change in momentum is equal to the mass of the object times the change in velocity. and so the force applied on an object times the time of contact is equal to the mass of the object times the change in velocity. If you decrease the time of contact between the bat and the baseball, you will greatly decrease the change in velocity. This is how a bat works. When applying the bat, the ball touches the bat for a very short time, creating a small impulse. This leads to a small change in velocity of the ball. If you increase the time of contact of the bat and the ball, you will then increase the impulse, which increases the change in velocity of the ball. Newton's third law. Until now, we have learned the first and the second laws of motion. Have you ever wondered why a bicycle moves forward? It moves because of the Newton's third law, which says that for every action there is an equal and opposite reaction. And see what happens when you drop a tennis ball. As the ball hits the floor, it causes a downward force on the floor. This is the action. The floor reacts by pushing on the ball with the same force but in the opposite direction. Action, reaction. Together, the floor and the ball forms what we call the action-reaction pair. So now applying on your bike, when you push the pedal, the part of the tire in contact with the ground pushes the ground backwards. The ground in turn pushes the tire forward with the same force. So the tire and the ground forms an action-reaction pair. But why doesn't the earth move backwards when you push it? Because the mass of the earth is much larger than that of the bike, and thus the force applied by the bike cannot move it. Conservation of linear momentum. Look here. We have many microbeads which provide a very low rolling friction for these metal slides. A rubber band is being used to attach the slides to a launching mechanism. It's got tension, so when it's cut, it will launch the metal slides. When the rubber band is cut, the metal slides move apart due to action and reaction forces. Each metal slide will receive an acceleration depending on its mass. If the duration of the separation is t, the impulse given to m1 is minus ft, and the impulse given to m2 is plus ft. The impulses are equal to the corresponding change of momentum for each body. That is, minus ft is equal to minus m1 v1, and plus ft is equal to plus m2 v2. Adding the two, plus ft plus minus ft is equal to minus m1 v1 plus m2 v2. ft's disappear and we shall have m2 v2 plus minus m1 v1 is equal to 0, and therefore m2 v2 is equal to m1 v1. Therefore, momentum before interaction equals to the momentum after interaction. Now, to illustrate this further, I will give the blue ball on the left some momentum by removing the platform. And now it bounces off the other ball and then comes off again. And so, is linear momentum conserved? Yes, it's always conserved in every collision. I have momentum on the left side and transferring that to the right side, and then it's simply coming back again. And this only works if they both have the same exact masses. But what would happen if I made it of different materials? Let's say I made it out of clay. What would happen? What happens is that instead of just bouncing off, they are connected with each other, and so what's lost is that we are losing some of that speed. We still conserve our linear momentum, but we lose some of that kinetic energy. So conservation of linear momentum occurs in collision between two bodies. So if two objects run into each other, the momentum we had before the collision equals to the momentum after that collision. So let me set up some little elastic collision like that. We are transferring momentum from one object to another. We call this elastic collision. Why is that? not only do we maintain our linear momentum, but also have conserved that kinetic energy. No loss of speed. In other words, the kinetic energy that came into the system equals to the kinetic energy that came out. We could also have another type of collision called inelastic collision, and that's when one object hits another and they lose some of that kinetic energy. Maybe they become connected or run into a wall where they completely stop. We call that an inelastic collision. Did we maintain the conservation of linear momentum? Sure we did. We always do in a collision. Did we maintain the kinetic energy? No. We've lost some of that speed. Did we maintain energy? Is there conservation of energy? Yes. Where did that energy go? It became internal energy inside the objects. And so the illustrations can be summed up in a law known as the law of conservation of linear momentum, which states that for a system of colliding bodies, the total linear momentum remains constant, provided no external forces act. Let's take an example. A bullet of mass 5 grams is fired from a gun of mass 0.5 kilograms. If the muzzle velocity of the bullet is 350 meters per second, determine the recoil velocity of the gun. Now in the solution, both the gun and the bullet are initially at rest, and therefore the initial momentum is 0. Momentum of the bullet after firing is given by mass times velocity. 0.005 kilograms times 350 meters per second gives us 1.75 kilogram meter per second. But momentum before firing is equal to momentum after firing. Therefore 0, the momentum before firing, is equal to 1.75, the momentum of the bullet after firing, plus we need to find the momentum of the gun after firing, which is given by mass times velocity. So we shall have 0.5 v, where v is the recoil velocity of the gun. Thus 0.5 v is equal to minus 1.75, and v is equal to minus 3.5 seconds. The recoil velocity is therefore 3.5 meters per second. Elastic and inelastic collisions. Let's say we take a ball that has a 10 joules of potential energy and simply drop it on the table. Now probably it won't do that, but if it did, it will be a completely elastic collision. We converted that potential energy into kinetic energy, and as it bounced off the table, it returned all that kinetic energy back into the ball, so it was able to get back again. Now let's take another ball made of different material and drop it. It doesn't bounce at all. We call that a completely inelastic collision. Where did the energy go? Where did the 10 joules of energy? They became internal energy in the table and the ball itself when they collided. Now we know most balls will be somewhat in the middle, somewhat elastic and somewhat inelastic. And so in any collision, it could be elastic or inelastic, we will maintain the linear momentum. In other words, the momentum of the object before the collision will be equal to the momentum after collision. In an inelastic collision, not only do we maintain the linear momentum, we also maintain the kinetic energy. The speed before the collision equals to the speed after the collision. In an inelastic collision, we still maintain the linear momentum, but we've lost some of that kinetic energy. Where does the energy go? It becomes internal energy. And so let me show some collisions between model cars. Okay. There are two collisions there. One is elastic and the other inelastic. Could you tell which one? We call that elastic and that inelastic. So for elastic collision, we conserve the kinetic energy, But for inelastic collision, some of the kinetic energy goes into the internal energy. And so if you think of real cars colliding, there's lots of damage, and that's because of the internal energy that used to be kinetic energy. Let's do some elastic collisions. We have a 1 kilogram car traveling at 5 meters per second to the right, and we also have another 1 kilogram car traveling at 2 meters per second again to the right. They will bounce off each other, and now we have some new velocity. Was linear momentum maintained? It's always maintained in collisions. But let's see that working out the conservation of linear momentum. Momentum before must be equal to total momentum after. m1v1 plus m2v2, that is momentum before, must be equal to m1 prime v1 prime plus m2 prime v2 prime. 1 kilogram times 5 meters per second plus 2 kilogram times 2 meters per second is the momentum before. Does it equal to the momentum after? If we multiply, it's 9 kilogram meter per second. Now the positive momentum indicates that it's a net momentum towards the right, and it's equal, and will always be equal. But did we maintain the kinetic energy? So kinetic energy before has to be equal to the kinetic energy after, and we have the formula: kinetic energy is equal to a half mv squared. If I key in those values, what I find out here is that the 16.5 joules that I had before the collision equals to the 16.5 joules that we have after the collision. This is an elastic collision. Let's now deal with an inelastic collision. These two cars will come and connect with each other when they collide. Then this formula of conservation of kinetic energy is useless to us. It doesn't help us at all, and we can use the conservation of linear momentum. So we write it out. This is momentum before and then momentum after. You can see that in this case, the cars will be connected, and so the velocity of both of them after is going to be the same. And I wrote this as V3. This is our new shared velocity. I punch in my values: 1 kilogram cat going at 5 meters per second and 2 kg cat moving at 2 meters per second before collision. After, the masses don't change, and so I can solve for that V3. I can solve for a velocity of 3 meters per second. And so in an elastic collision, that shared velocity allows us to solve for the change in linear momentum. Let's make sure that that works. Yes, they both have 3 meters per second. An example: a bullet of mass 10 grams traveling horizontally at a speed of 100 meters per second embeds itself on a wooden block of mass 990 grams. Calculate the velocity of the bullet and the block immediately after collision. In the solution, let v be the common velocity of the block and the bullet after impact. Since momentum is conserved, momentum of the bullet before collision, 10 grams, that is 0.01 kilograms, times velocity, that is 100 meters per second, plus momentum of the block before collision. The block is at rest, so we shall have mv 0.99 kilograms times 0 should be equal to the momentum after collision. That is 0.99 plus 0.01 times v. So we shall have 1 plus 0 is equal to 1v, and v is 1 meter per second. So the common velocity is 1 meter per second. True and apparent weights. The weight or true weight of a body is equal to the force exerted by the earth on the body. The true weight of a body of mass m is given by weight is equal to mg. The weight of a body is measured using a weighing machine or a spring balance. When a body is kept on the platform of a weighing machine, its weight is given by the normal contact force between the body and the platform of the machine. Similarly, when a body is suspended from a spring balance, its weight is given by the normal contact force between the spring and the body. When the body is placed on the weighing machine, the forces acting on the body are the force of gravity or its weight W acting vertically downwards, the upward normal contact force N exerted by the platform on the machine. It is this upward normal contact force exerted by any supporting surface which gives a feeling of weight. This normal contact force is called the apparent weight of the body. The value of this apparent normal contact force N depends upon the state of motion of the body. To understand the concept of apparent weight, let's imagine a person standing on a weighing machine placed on the floor of an elevator. Observe the position of the pointer of the weighing machine when the elevator is at rest. When the elevator moves downwards with a constant acceleration. When the elevator moves upward with a constant acceleration. And when the elevator falls freely. We observe that the apparent weight registered by the weighing machine is equal to the true weight of the body, less than the true weight of the body. More than the true weight of the body, and equal to 0. That is, the apparent weight of a body depends upon the state of motion of the body. When the elevator is at rest, the person inside is also at rest. External force is equal to 0. Thus, the true weight of the body W acting normally downwards is equal to the normal reaction force acting vertically upwards. In this case, the machine registers the true weight of the body. When the elevator moves downwards with a constant acceleration A, the net force acting on the person is equal to the true weight of the person minus the normal contact force. N is less than mg, that is the true weight of the person. Thus, the scale reads less than the true weight of the person. When the elevator moves upwards with a uniform acceleration A, net force acting on the person is equal to the true weight of the person minus the normal contact force, and it's greater than the weight of the body. Thus, the scale reads more than the true weight of the body. When the elevator falls freely, that is when cables break, both the person and the weighing machine fall with the same acceleration. mg is equal to mg minus n, or n is equal to mg minus mg, which is equal to 0. Thus, the apparent weight of a freely falling person or object is 0. That is, a person or an object appears weightless when falling freely under the influence of gravity. Thus, during the state of weightlessness, the force of attraction due to gravity does not become 0. Rather, it is the apparent weight of the body that becomes 0 during the state of weightlessness. Friction. If you gently push a block on a table, it moves a distance, then stops on its own. If you push it from the other side, the same thing happens. It stops. As you can imagine, a force must be acting on the block opposing its motion. This is the force of friction. If you apply a force along the left, friction acts along the right. If you apply a force along the right, friction acts along the left. In both cases, friction opposes the motion of the wooden block. Friction force always opposes the applied force. In this case, friction acts between the surface of the wooden block and the surface of the table. Friction is caused by the irregularities on the two surfaces in contact. Even surfaces that appear very smooth have minute irregularities on them. Friction is caused by the interlocking of the irregularities on the two surfaces. It is obvious that friction will increase if the two surfaces are pressed harder. If you try to push a box at rest, you realize that it is tough to get it started. The force required to overcome friction at the instant an object starts moving from rest is a measure of static friction. The force required to keep objects in motion is a measure of kinetic or sliding friction. When the car starts moving, the irregularities between the rod and the tire do not get enough time to lock, so the sliding friction is slightly lower than the static friction. Look at this. I want to pull a large load of blocks and I want you to watch the spring balance. It increases, the blocks do not move. Suddenly a threshold is reached and I can pull the load with less force. Important to know is that friction is independent of the area of contact between two objects. However, friction is directly proportional to normal reaction R. So F is proportional to R and therefore F is equal to mu R, where mu is a constant called the coefficient of friction and depends on the surface in contact, and R. Mu subscript K is the coefficient of kinetic friction. Mu subscript S is a measure of static friction. An example: a wooden box of weight 300 newtons rests on a rough floor. The coefficient of friction between the floor and the box is 0.6. Calculate the force required to just move the box, and if a force of 200 newtons is applied to the box, with what acceleration will it move? Take acceleration due to gravity g to be 10 meters per second squared. In our solution, frictional force is given by F is equal to mu R. R is the reaction force, which is equal to the weight of the box. Mu is 0.6, so we have 0.6 times 300, which gives us 180 newtons. B. The resultant force is equal to 200 newtons, the applied force, minus the force required to overcome static friction, which gives us 20 newtons. So we shall have, from F is equal to ma, 20 newtons is equal to 30A. A is equal to 20 over 30 and it's equal to 0.67 meters per second squared.